Well, hello, Calculus students and seekers of truth. We continue here our study of sequences and series. And now we're going to talk about the formal, rigorous definition for convergence and divergence of a sequence and then of a series. So here I've set up some terminology here and some examples. So let S sub n be the nth term of the sequence S. So let's say here's our example n here, if n was 1, right? So if s is 1, that's equal to 1/2. S is 2, that would be equal to 2/3. Okay, so all n here is indicating is the particular order or the order that the term appears in. Okay. If the limit as n approaches infinity, so like the trillionth term, right, of S sub n is equal to k, where k is finite, then we can say that S sub n converges. Sorry, this should say S converges, and S sub n too, but what I really mean to say is that S converges. Otherwise, S diverges. And one of the ways that we can approach this and these examples is to maybe find like a formula for S sub n. This is like very, very important. And you can see here in this particular example, S sub n is nothing more than n over n plus 1. Right? So here I have a collection of fractions where the numerator is the nth term, is the same as the term, and the denominator is just one bigger than that. And what we want to figure out here, well, what is the limit as n approaches infinity of S sub n? Well, that's the same thing as the limit of as n approaches infinity of n over n plus 1. And you can see here pretty clearly, just using what we know about asymptotic behavior, you have a linear function of n on top, a linear one on the bottom, and this is going to approach 1. And so as these numbers as we get more and more terms, right, 1/2, 2/3, 4/5, 5/6, we get closer and closer to 1. We never actually reach 1, but if we go really, really large, you end up with a trillion divided by a trillion and one. So that's going to be like 0.99999 something. So here we can say that S definitely converges. All right. In the next example, we have something maybe a little bit different, but not too different. Our series R here. And so R1 is 2, right? R2 is 2.1. And you can see here, all we're doing is just adding a tenth each time. And so it's not too hard to figure out this formula. R sub n is equal to 2 plus 0.1 times n. And maybe here we can qualify, we can say that n is greater than or equal to 0. So we're going to start out with 0. And so remember what I said before, when do we start these terms? So maybe we should amend this and we can say that uh, instead of starting at 1 and going up to 2, R sub 0 is 2, R sub 1 is 2.1, and this will help us to satisfy this formula. Now, it doesn't change what the series is, we just redefined it a little bit differently so that the formula works a little bit more conveniently for us. All right, so now we want to take the limit as n approaches infinity of R sub n. Right? So that's the same thing as 2 plus, or the limit as n approaches infinity of 2 plus 0.1n. Now here, this part is important because if n is very large, if n is 10 to the 45th power, right, then this sequence is just going to keep on growing and growing and growing. And so this has no limit. It's going to approach positive infinity. And so we can say that R diverges. All right, now let's take a look at one last one. It's a little bit different, maybe a little bit challenging. G is equal to -1, +1, -1, +1. We can actually figure out what this is. This formula, G sub n, would be equal to -1 to the n, right? So we're basically just raising -1 to a power, and we can qualify this. Actually, n does start out at 1, right? So the first one is -1 to the first, -1 to the second, -1 to the third. And when we take this limit, well, this is something that's a little bit different and it's kind of interesting. Um, what does this approach? Right. Well, it's going to approach either -1 or +1, but the strict definition is that the limit has to approach a number, not several numbers, not lots of different numbers, a singular number. And so in this case, k is finite, but we have like too many k's. We have two numbers that it could be bouncing back and forth. And in this case, it's really not approaching anything. Approach means it gets closer and closer as you move as you move down and get more and more terms. So in this case, even though it may seem counterintuitive, we can say that G diverges. This is a kind of a famous sequence. It's called Grandy's sequence, and we can talk about it when we a little bit more when we discuss uh, the convergence and divergence of series. Okay. All right, so there's a very, very brief and quick introduction review, I hope, into this determining if a sequence will diverge or converge. And basically, you're just looking at the pattern as you have more and more terms, do you get closer and closer to a particular finite value? If you do, you have convergence. If you don't, it's divergence. Thank you for watching and have a wonderful day.